Okay, I think we can go ahead and get started now. And we're going to pick up where we left off last time about training neural networks in practice. So we'll do that first, and then we'll take a bit of a pause to talk for a bit about the class project and answer any questions that people might have. And then we'll start back up again with object detection. And so today we'll be talking about object detection and related models from kind of the standpoint of the architectures that you use. And then next lecture, we'll talk about these kind of in a very practical way in terms of how you would actually implement them and the things that you need to watch out for. So going back to where we left off last time, if you remember, we talked a little bit about loss functions that were used for classification. So essentially there's two, the softmax and the SVM hinge loss. And then we talked about a variety of issues that come up when you're actually trying to train these neural networks in practice. We talked about using the ReLU activation function, about data preprocessing, which is very simple with images. You just need to essentially subtract out 3 means in each of the channels. We talked about initialization and why it's important to be careful about how you initialize and how you should initialize. We talked about how to actually optimize neural networks and about the different solvers that you could use. And then we talked about regularization. And so, using the regularization term in the loss, dropout, batch normalization, and how that helped with a variety of challenges in optimization, making the space more smooth, helping with covariate shift, and also introducing regularization in and of itself. And we stopped with dropout. And so now we'll pick up with data augmentation, also as a potential form of regularization. And so what data augmentation means is you take your labeled data and you transform it such that labels are preserved. And so the examples in the literature, which were kind of designed around natural images, are things like take random crops of the image, flip the image. So if you have a cow and it's looking left, you flip it so the cow is now looking to the right side of the image. Randomly varying the contrast and the brightness of the image, rotating, stretching, lens distortion. By and large, these weren't developed with documents in mind. And so if you're processing documents, you might kind of not get quite the results that people get, when they're processing natural images in the literature. And we'll come back to this, later in the course. But kind of in general, you take these and you apply them to your labeled data, and then you train on the augmented data. And the reason that this helps to regularize is, it goes back to the paradigm of this idea that regularization can be anything that kind of adds noise to your training. And by adding these different types of random noise, it makes it more difficult for your network just to memorize your training data. And it makes it more robust, more extensible to other applications that you might see in the future. Data augmentation also has other purposes, like essentially, creating labels for free that we'll talk about kind of later in the course. But what's important to note here is that this can actually be used as a way to regularize the data. And so, for example, when AlexNet won the ImageNet contest, it used made very heavy use of data augmentation, essentially as a way to keep the model from overfitting. Okay, another topic that we'll mention just briefly here in terms of training that's very, very important is transfer learning. And so transfer learning is just when you take a network that somebody else has already pre-trained. So you could take ResNet pre-trained on the ImageNet data, and you use that. And so, at one extreme, you might just freeze all the convolutional layers and just train your own classifier head on the end of that, like say you don't have very much data. At the other extreme, you might allow all the weights of the ConvNet to update, but you just initialize with those pre-trained weights that came from training that data on ImageNet. And this is hugely important because usually when you see things pre-trained from scratch, it just takes a massive amount of data, right? So in the case of like CNNs, like ImageNet, you know, is, I can't remember exactly, something like a couple million training examples. It's a very large data set that takes a ton of compute to pre-train. You know, it's even kind of more extreme in natural language processing, where something like Google BERT, I mean, like, I don't even know, you know, how much data that Google used to pre-train that. It's very, very costly to have kind of that kind of compute. It takes a long time, but you don't have to do that because there's these model zoos that include models that are pre-trained. You know, for example, pre-trained on ImageNet or pre-trained on Coco. You might also go further than this. So let's say that you're doing object detection on documents. You might want to start with model weights that PubliNet, which is like a benchmark data set for document object detection. You know, PubliNet itself took you know, the pre-trained data from ImageNet and then fine-tuned it to work better on documents. Let's say you have documents and they're pretty different than the Publi documents, which are like modern, you know, journal articles. And so you can't just use PubliNet off the shelf. It'll give you garbage or, you know, nothing at all. But you can take the pre-trained or, you know, the fine-tuned weights from PubliNet and use that as your starting point, and you're going to converge probably a lot faster. So this is something we'll talk about a little bit more next week when we talk about, you know, fine-tuning and practice. But in general, when we use the term, you know, pre-training, that means we have a whole bunch of data and we take a network and we pre-train it from scratch. Whereas with transfer learning, you take something that's already been trained and you fine-tune it. As I was saying, you know, exactly how you do that is going to depend on your application and on how much data you have. You know, so at one extreme, you might want to do something that's pretty similar to the pre-trained model, and you have just a very small amount of labeled data. So in that case, what you might want to do is just freeze all the earlier layers of the network. Because remember, like when we talked about convolutional networks, remember our motivation that, you know, the first layers are doing something pretty general in that they're picking out things like edges from pixels. This is pretty generic. Whereas you get further and further into the network, they're picking out these, they're taking those edges, etc., and they're assembling them into more complex features. And this is getting more and more task specific. And so in general, the later layers of your network are very specific to whatever it's been kind of pre-trained on, whereas the earlier layers are more generic. And this will be a theme. We're going to come back to this theme in natural language processing, where people have kind of tried to probe this and understand this. But this intuition, it works very well. And so if you're doing something that's pretty similar to what you pre-trained on, you may just be able to freeze like those earlier layers. And just pre-train the classifier or the final layers, and that's going to take less data. On the other hand, your task might be pretty different, so you might want to be able to allow all the weights to change, but just starting from the weights, the pre-trained weights is going to help you to get there faster. Another thing is that you want to set your learning rate lower for fine-tuning than you would if you were pre-training from scratch. So kind of a rule of thumb is 1/10 of what it would be for pre-training. And the reason is, like, if you're pre-training from scratch, you're just starting from this random initialization, and you're probably not very close to your local min. Whereas if you're fine-tuning, kind of the idea is, well, somebody's already got this in a reasonable place, and your data, your application's a bit different, but you're probably close to where you want to go, and so you want to learn at a slower rate. Okay, which brings us to the question of how to set hyperparameters. But before I go into that, are there any questions about what we've covered so far? Okay. So setting hyperparameters, We'll talk about this some more next week when we talk about object detection in practice. But this is, these hyperparameters are really, really important. And so generally speaking, like if you go and you look at a benchmark data set, they'll have 3 partitions of the data. So there's the training set, which is what you train the network on, the validation set, which is what you use to cross-validate to choose your hyperparameters. And then there's the test data set, which is what you look at only kind of at the very, once you've decided what your architecture is, and that's what you report in the paper. I think like, for our applications, if we're not writing computer science papers, this is kind of like a bit less relevant, because our goal is not to say like, oh, like I have a model with 0.8 accuracy on the test data, but rather just to do as well as you can on the inference on the unseen data, but you might still kind of partition things in this way. So you need to cross-validate across your hyperparameters. Obviously you cannot, there's a lot of hyperparameters, and like there's even more when we get into object detection as compared to like classification. And you can't obviously check all combinations of all hyperparameters, because that's a problem that grows exponentially, right? In general, the most important hyperparameter that you need to validate, along with the architecture itself, is the learning rate. It's super important. And so you see here, I like reproduced this tweet where this guy, Andre Karpathy, who's kind of a leading AI researcher, says, oh, 3e⁻⁴ is the best learning rate for Adam, hands down. And then he says later, I just wanted to make sure that people understand that this is a joke, right? Which goes back to a more general point that like what your learning rate should be is going to depend on your problem, and you really need to do some cross-validation to try to get it right. So when you're doing this cross-validation, you wanted to test different parameters. You might think that you would do that like in a grid search, like you're varying your learning rate along a grid, and then you're varying some other parameter along a grid. But it turns out you don't actually want to do that. And the reason for that is that usually it's going to be the case that some parameters are much more important than others, right? So maybe your learning rate, everything's really sensitive to your learning rate, but the regularization parameter that determines the weight on that regularization term in your loss, it's not so sensitive to that. And so you can see, if we're going to search 9 points, in the figure on the left, you actually miss, what the optimal parameter for the optimal value for the important parameter would be. Whereas when you do this random search, you're just able to span more of your range, and you're able to see that, more values of what will probably turn out to be the important parameter. So just in practice, when you are doing cross-validation with hyperparameters, sample your space randomly rather than with a grid. Okay, and so let's talk about optimizing the learning rate specifically, since that's the most important thing. And so you want to begin with a very coarse search, and you don't need to run the whole model through to convergence. If you do just a few epochs, which means like seeing all your training examples once as an epoch, if you do just a few of those, you're already going to see learning rates where bad things are happening. And so with that, you can kind of get rid of the ones that don't make sense, and then you can do a finer search. An important thing about the learning rate, right, is the learning rate is multiplicative. And so like basically you multiply your gradient step by the learning rate, and because it's multiplicative, that means you need to search in log space. Don't search in non-log space. And just worry about getting a good learning rate first, and then you can worry about learning rate schedules, which you may or may not need depending on sort of what method that you're using. So like, as we talked about last class, a method like Atom for optimization is already adapting the learning rate. And so there it like is kind of less central to have this adaptive learning rate schedule, but people kind of differ on whether they think it's still desirable. And so to understand this point, you know, you see here, like I've plotted the loss as the model advances. And you can see like there's a very high learning rate. That's a bad idea. You're going to diverge because remember we saw earlier on Monday, when you have a very high learning rate, you actually bounce and can like move away from the optimum. If you have a low learning rate, maybe you'll get there eventually, but it's going to take a long time. And with a high learning rate, you may kind of plateau out. So you get somewhere and then you just bounce around. Which of these schedules is best? Well, that's kind of a trick question because ideally you would actually want to combine these. And so you'd want to start out with the high learning rate initially because your loss falls most steeply with that, and then you want to reduce it. And so that's called a learning rate schedule. And a common way to do this is just to have a step decay, where after so many epochs, you're going to just decay your learning rate by a preset step. But there's the, you can have exponential decay, different types of learning rate decay. But as I said, kind of worry about getting something that works reasonably well first, and then you can worry about the schedule. Okay, so just to sum up, the learning rate is the most important hyperparameter usually, and we'll talk about other ones next week. And they're going to be a little bit different what the hyperparameters are if you're just doing classification like we're talking about now versus object detection, which we're going to talk about in a few minutes. There's other hyperparameters. We'll talk about this concretely, but kind of no matter what you're doing, the learning rate is probably going to be the most important. Start with a static learning rate. Once you found something that works well, you can worry about a dynamic learning rate schedule. Some people say that kind of once you get the learning rate right, image classification tends to be less sensitive to other parameters. I think that's not necessarily so true for object detection where there's more things to worry about, but we'll get there. Okay, are there any questions about hyperparameters? Okay, and so you want to monitor your learning process. So how do you do that? You can plot your loss as well as plotting your accuracy. So remember, you have accuracy on your training data and accuracy on your validation set, which is what you're using to validate your hyperparameters. And so we should expect the loss to kind of be falling over time and the accuracy to go up over time. But this is like after each epoch, it's saving what the loss and the accuracy is. And so if you have a big gap between train and validation, that's suggesting overfitting, and you're going to want to go back and increase your regularization parameter, or maybe you want to do dropout or do something else that's going to increase regularization. On the other hand, if you have a very small gap between train and validation, that suggests that there's scope to increase the model capacity, maybe by adding more data, etc., changing your learning rate. Okay, so here is what a bad initialization would look like. If your loss is very flat for a long time and then suddenly it falls, it's because you started with a bad initialization, and you can kind of move to where you're at when that loss starts falling to initialize it instead. On the other hand, if the loss explodes, like goes off to like, what you'll see in practice is NAN, like it's gone off to infinity. That indicates that the learning rate is too high. You don't have to wait for it to explode. If your cost after updating is substantially larger than the original. Like let's say as a rule of thumb, it's 3 times or more greater than the original, you know that your problem is diverging and you can just stop right there because your learning rate's too high. Another thing that you would look at is the ratio between your update and your parameters. And as a rule of thumb, people suggest that be around like 0.001. Okay, so you can find a lot more suggestions out there online in the literature. There's a paper by he et al. Called Bag of Tricks for Image Classification with Convolutional Neural Networks. Usually people are testing out tips and tricks on things like ImageNet or Coco. So if your data doesn't look like ImageNet, right, which is like animals, vehicles, etc., natural images, your mileage with the tricks might vary. But nevertheless, I think it's useful to look at these because it gives you a sense of like the things that people try to improve performance. Okay. So are there any questions about that? Okay, so just to sum up, so activation functions use ReLU. Data pre-processing, you just need to subtract the mean of each channel. To initialize your weights, use he et al, or else start with pre-trained weights. Optimization, you probably want to use SGD with momentum / Nesterov, which is similar, or Atom. There's an entire big literature on which is better. I think so in general, Atom tends to do better, but that's not necessarily been true in ComNet. Some people will argue about this, but just don't use like plain stochastic gradient descent. Use batch normalization, and you also may need to use other regularization methods, like the L2 regularization we talked about. If you have fully connected layers, maybe consider using dropout, maybe consider using data augmentation. You need to think about how regularization methods may interact with each other and with the optimizer. So we talked about how it's not a good idea to use batch norm and dropout on the same layers, or about how L2 regularization will largely be undone with batch norm, about how L2 regularization is a bit different, like if you're using SGD with momentum versus Atom. And so it's just important to kind of keep those interactions in mind. And then when you're optimizing your hyperparameters, just follow the best practices that we talked about, like doing a random search, searching from coarse to fine, and really like focusing on getting the learning rate correct. Are there any questions about kind of this redux of training neural nets? Okay, so the last thing I want to say on this topic is about deep document classification in practice. And so this ends up being pretty straightforward, so we're not going to spend a lot of time on this. We'll spend a lot more time talking about object detection in practice. Again, when you go out and read the literature, it's kind of mostly motivated by using like ImageNet, which is natural images, pictures of animals, pictures of vehicles, etc. Oftentimes as economists, we may want to be classifying documents, and there is kind of like a small literature on this. And so you'll recall that kind of a theme is that the deep learning literature advances by comparing performance against benchmarks. And so there's benchmark data sets for all kinds of different tasks. And if you're doing something relevant to that task, you test how well you're doing on the benchmark. And so the benchmark data sets for document classification are called RVL-CDIP and Tobacco 3482. And so this is what these data sets look like. The first one has 400,000 grayscale images. They belong to 16 classes, which are shown here. And there's 25,000 labeled images per class. As you can see, these are things like letters, memos, emails, forms, questionnaires, resumes. And so these are documents that may not be like horribly relevant to your research. Like I think like a typical kind of like documentation, like classification problem that we had is we had these firm level reports and like a bunch of the pages were tables, but then you also had advertisements kind of randomly scattered in there. And so you needed to classify whether a page is an advertisement or a table. And so, you know, this might be a bit different than what we want to do, but this is what there is. This is what things have been evaluated on. The tobacco data set's essentially the same, but it's a lot smaller. It only has 3,482 images, which is pretty small in the context of deep learning. And it puts those into 10 classes that are kind of similar to the previous classes. And so there's papers on this, like a prominent one is called Cutting the Error by Half, Investigation of Very Deep CNN and Advanced Trading Strategies for Document Image Classification. They test a variety of deep CNNs that they've pre-trained on ImageNet for the purpose of classifying on these two benchmark document data sets, and they argue that VGG16 gives state-of-the-art performance. As always, your mileage may vary if your data don't really look exactly like these benchmarks. I think the thing is, if we go back to our CNN lecture, remember VGG16 it did pretty well, you know, not quite as well as ResNet on the ImageNet challenge, but pretty well, but it took a lot of memory, and it's because it had those fully connected layers at the end that had like, you know, 100 million parameters, more than that. Whereas, so the size of the circle is the memory required, and the x-axis is the number of operations. And you know, so I personally would probably use a ResNet backbone for document classification, just because it's like, you know, or at least I would start there. And if it wasn't getting me what I needed, I might see if VGG worked better, but this is much more expensive. And like, maybe it's like, okay, like if you have your own GPU and you're not doing a bunch of other stuff on it, you know, if you're paying to rent a GPU from like Azure or AWS, then you might care a lot that this is a bigger model. So I'll just kind of end with that. So you know that this is what is argued to kind of be state of the art. And it's even kind of, there's been some more recent things. Some people argue this is still true. But in general, like ResNet is a pretty good place to start. I saw that Google Scholar kind of has their citation metrics, and like ResNet was like, had more citations than any other paper that exists in 2020. So a lot of people are using this, and then there's good implementations of code for it out there. And I think you kind of can't go wrong by at least trying the ResNet backbone. Okay, so I'm going to stop this. Are there any questions about document classification? Okay, so now we're going to continue with thinking about object detection, which is another major task in computer vision, and it's one that I think is, you know, probably the most relevant computer vision task to us as social scientists. Obviously, you guys have all kinds of creative ideas, and you may use different types of methods, but this is particularly relevant. But before I get there, I wanted to talk a little bit about the class projects. And so central to the course is the class project. And the general aim of it is to allow you to apply whatever methods seem most relevant to your research to a very concrete problem, which just gives you kind of more of a sense of the issues you're going to have to face in practice than just doing like a contrived, you know, problem set or whatever. And we're here to kind of help guide you through those challenges and help you to get this hands-on experience that hopefully will help you with your research moving forward. And so if you don't you don't have a sense yet for which of these methods are going to be the most relevant to your research, that's also completely fine. And so when we get to NLP, you'll see that it has like a lot in common with computer vision. So, you know, I would start by thinking, you know, am I more likely to want to process images or text? And if you don't really know the answer to that, or you think they're both of relevance, it's completely fine because the methods are actually very similar. And in practice, you might oftentimes be processing both of those. And the great thing is you're not starting from scratch with NLP because they're both built upon deep learning. If this helps you with a concrete, research idea that you're already working on, that's great. But that also isn't necessary. The most important thing is to get hands-on experience designing and implementing a deep learning pipeline. And so if you kind of have no idea where you want to start, you can come to us and we can always kind of give suggestions. As it says on the syllabus, you're free to work in groups. That could be with others in the course. It could be with people outside the course or on your own. But if you are working in groups, I would encourage each person to have a distinct part of the pipeline that they're responsible for. Because again, really the point is to give you kind of that hands-on experience with these methods. It's one thing to understand them in theory, but you want to be able to actually implement them, and hopefully by having you implement them in this course, we can save you guys some effort on, versus implementing them later on when there's nobody to kind of get advice or guidance from. One thing that you need to keep in mind, and we're kind of more than glad to help you assess, is that you need to consider what compute you can access, because a big data project can obviously pretty quickly take a ton of compute, and cloud GPUs are pretty expensive. And so, as we discussed before, Azure provides $100 in free credits to anybody with a .edu address who signs up. I've been kind of pushing the university to do something in this regard in terms of giving students more access to compute, which is not happening now with all the COVID budget cutting everything. So this is kind of essentially what there is. If you're in the economics department and you need compute for a project, we do have various grants, and I'm more than happy to kind of write people a letter for that. If you have a research idea and this is going to be kind of part of a research project, there is kind of some funding out there. If you think that deep learning is going to be a big part of your research, I really encourage you to try to find funding to get a GPU, and you can get a pretty basic one for a pretty reasonable price compared to what it would have cost a few years ago, because the cloud is great. If you're not going to hardly ever use this, or B, if you have to process like 10 million images and you want to do it in parallel on a bunch of really cheap CPUs. That's kind of what the cloud is good for. And then the other thing that the cloud is good for is being easy, because we'll talk about next class, the biggest headache of implementing any kind of deep learning pipeline is dependencies. And these packages constantly get updated and then everything breaks because your dependencies break, and you have an OS update, it's going to break everything. And if you're using AWS, they kind of take care of that for you, but they charge a really high markup to do that. So again, if this is going to be central to your research, I do encourage you to try to find resources to get a GPU. I mean, I know in kind of the economics department, we have some general funds for students, but a lot of the way our money works is there's funds around specific research ideas. And so if you have a research idea in political economy, there's one fund. And if you have a research idea in macro, there's another fund. So it's kind of if it's good to talk to faculty in whatever your research area is, and they can give you a bit of a sense of kind of what the resources are. But coming back to the class project, we're just going to help you evaluate if you want to do something that's going to be super costly, we'll try to figure that out early on. Okay, and on that note, there's 4 different assignments around the project. And so the idea of the first report is just to tell us what are the raw data you hope to process, what output do you hope to get, and if you have any thoughts on the relevant methods, please include those and we can provide feedback. And so I know your project may be about NLP and we haven't gotten there yet, so you have no idea what you want to do, and that's fine. We can also kind of help to point you now in the right direction. If you have more than one idea, and you're not sure which is best, you can talk about that. Just like, keep it to a reasonable number. Like, we can't really provide detailed feedback on 10 ideas, but if you have a couple of ideas, that's fine. And so the goal of the first report is just to kind of figure out, like, is what you want to do feasible? And if it seems like something that's just going to be too difficult or kind of too out of scope to do for a class project, we'll try to kind of help point you in a more feasible direction. The second report, we'd like to have a more specific roadmap for what your data processing pipeline is going to look like. And even if you're not for sure, kind of do your best to figure out, this is what my pipeline is going to look like. Step 1, step 2, step 3. The third report, any progress on implementation that you have is great. If you have any challenges, then just, and you're not sure how to solve them, ask. We may not have any idea either. We just have to tell you to kind of go and keep looking, go ask someone on Reddit, which can be like a good source of information. But if we have any idea, like, we'll also try to provide you feedback. And then the final report, submit a final product. So I imagine for most people, kind of what your project will be is like processing a data set. You have some raw data and you have some output data that's computable that you can go and run analyses on. For this class, you don't need to run the analyses. This is just about, getting the data, but you can. You certainly can do that. And so the output in that case might be like a data appendix for a paper. Pretend like you're using this in the paper and this is your data appendix to describe how you produce this data. A GitHub repository with the code would be good to include. Some other people, depending on your background, might be interested in producing an open source project. So the idea there is you make a tool that then other people can use. And so that's not expected. But I do know that there's some people with kind of a strong background who are interested in doing that. And in that case, your open source project might be your GitHub page with the code, and there's going to be some documentation there. And then you might have a web page that describes your tool. So in the open source community, it's really important to kind of have that web page to publicize what you have. Again, you can go post it on Reddit or Twitter or wherever and make sure people know about your tool and use it, and maybe contribute to it and help make it better in the future. And so kind of those are the main things that we have in mind. If it's something that just, like, as I said, a good outcome is like, this is a type of data I'm interested in, and I'm going to use existing methods and process it. And so that's a great outcome. If you do end up doing something kind of more novel that we think is like going to be kind of a broader contribution methods wise that other people might want to use, we can also talk about, could you write this up as a CS paper? Do we know any CS students or anybody who would be good collaborators on that? That's not kind of the thing that you should be aiming for, but that's also a possibility to think about, kind of depending on what you do. Is there actually like kind of a broader methods contribution here? And so few people are using deep learning for social science data that there's a lot of scope to write those kind of papers. It's not kind of going to be the main goal of anybody who's an economics PhD student, but it's also a lot easier to write a CS paper than an econ paper. And if you have a great idea, you might as well put it out there. And I do think that you get at least a little bit of credit for that. People at least think you're really technically proficient and stuff when you go on the job market. So I'll just kind of throw that out there as something that, it's not necessarily like what we're aiming for, but that's a possibility. Okay. So now, are there kind of any questions about any of this? Okay, so hopefully it's clear. And as I said, really the goal is to just to help you guys to get hands-on experience, to resolve challenges that are likely to come up. If you get data out that you ultimately end up using for a paper, that's awesome, but that's not required. Okay, And so now I'm going to move on for the final 30 minutes to talking about some other computer vision problems. We probably won't finish this today, but that's fine. We'll start on this today. We'll finish whatever we didn't get to next week, and we'll also talk next week about how you implement these things like in practice. It's one thing to understand the theory, but now you want to go implement it. What do you do? Okay. So remember that at the core of almost all computer vision problems are Rcnns, which essentially take these spatial filters, which are just weight matrices, and they slide them across the features maps to connect different layers of the network. And so this is at the core of everything that we're going to do. It's going to build on top of this. So object detection, which is finding specific objects and images, as with other computer vision tasks, has been transformed by deep learning. And so this is another contest. This is a data set called Pascal VOC, which is an object detection data set that goes way back in time. And so this contest started in 2007. Nowadays, people don't really use this anymore because we solved this data set. Now people use a data set called Microsoft Cocoa, but that's much more recent. And so you see, like, going back before deep learning, we're going to talk about what mean average precision is in a bit. People are getting like a mean average precision of like 15%, or really at best like 40%. Which is essentially unusable. Like, we just couldn't really detect objects in images in the pre-deep learning days, and that has like completely changed. And you really see like there's an inflection point there using deep conv nets. And this figure just is from a paper. It only goes to like 2015, but it kind of on this data set it gets better until this data set is solved and people move on to something more challenging. And so we're going to talk today about a series of related computer vision problems. And so the one that's most central for us, I think, as social scientists, that you're the most likely to need to use is object detection, which is their kind of the third thing. And so you see this is a natural image. And in this image, there's 2 dogs and 1 cat. And you want to separately identify each of those objects of interest: the first dog, the second dog, and the cat. And those are 3 different objects. And then there's a background, and you don't care about the background. In this image, you're looking for dogs and cats. And so, by and large, as economists, we're probably not looking for dogs and cats. We probably have an image of a document, and we're looking for like cells in a table, or we have an image of a newspaper, and we're trying to detect articles, headlines, captions, images. That's also an object detection problem. So basically, kind of like any processing that you want to do of documents, what's in a document is going to boil down to an object detection problem. And the key thing about object detection are that there are objects and there's multiple of them, and you don't know ex ante how many there are. This image has 2 dogs, but a different image could have had 3 dogs. Okay, so that's object detection. But in order to understand object detection, we need to talk about a couple of other problems. So one is classification and localization. And so far in the course, we've been talking about classification, which is just that you have an image and you classify what kind of image it is. Like, so an ImageNet, it's like a cat, a dog, a car, an airplane. With localization, you do that, but you also want to draw the bounding box in the image for where that object is. And so this is a cat photo, and you want to identify the 4 coordinates of the box that surround that cat. And so this is essentially object detection, but there's only one object. Or there could be more than one, but you know exactly how many there are. And we'll see this is an important difference. If you have a pre-specified number of objects versus an unknown number of objects, that's going to change in a pretty major way how you solve this problem. Okay, there's also something called semantic segmentation on the left. And so in semantic segmentation, you take the pixels of an image and you put them into different classes. And so in this one, there's a grass, there's cat, there's trees in the sky. And every pixel you say, is it a cat? Is it grass? Is it tree? Is it sky? And in this case, let's say you have 3 dogs. You're not going to separately detect each of those dogs. They're just all dog pixels. There is no sense of objects here, separate instances, we say, separate objects. And this is something like, Zoom backgrounds, right? Is like doing segmentation. And again, I think that this may come up in some economics applications. It's probably not as common as object detection, but it uses methods that become relevant to object detection. So we need to understand this too. And then finally, there's instance segmentation, which is kind of like semantic segmentation, except each object is a separate kind of category. So again, you're recognizing like kind of the pixels, but each dog is a separate dog. And so it's essentially like, it's also similar to object detection, except instead of drawing a box around the dog, you're identifying exactly what pixels are a dog. And again, this is probably less relevant to us with something like documents, because if you have like cells in a table or articles in a newspaper, it's just like the object is a box. And so you don't need to know exactly what pixels belong to it, but it's actually straightforward to understand how to do this once you understand the other things. So these are the 4 things that we're going to talk about today. Okay, so we're going to start with semantic segmentation. Remember, semantic segmentation is taking each pixel in an image and figuring out on a pixel by pixel basis what category is that pixel. And now you get out of it these like masks. Okay. And so just the overview, we want to classify all pixels. We're going to do that with fully convolutional models where we downsample and then upsample. And these models are going to be learnable throughout. This differs from instance segmentation, where we want to detect individual objects. And that's going to look a lot more like object detection. So we're going to talk about instance segmentation at the end after we talk about object detection. Okay, so instance segmentation is actually a pretty old problem in computer vision. Like old means people were working on it before deep learning. And so initially, even early in the deep learning days, what people did was to use an approach that's called a sliding window approach. And they just treat it like a classification problem with these sliding windows. And so you see there's an image of a cow on the left, and people just take a box, which is centered at a pixel. And then you crop that little box. And you look at the pixel in the middle and you classify cow or not cow. And you do that for every pixel in the image, right? You just slide this window across, and each time you're asking, is it a cow or is it grass, trees, or sky? And so you're just treating this as a classification problem on each of these crops, where you're kind of trying, the ground truth is what the pixel at the center of that crop is. And like everything that we generally talk about with images, this is a heavily supervised problem, right? You know the ground truth. You have labeled data of these masks, and you're trying to train a model on that. And so this is actually a really problematic approach once we have deep learning, because it is super costly. And so you're having to run every single patch that you've cropped here independently through your ComNet classifier. And that's very costly. You're passing kind of each of these crops through this deep neural network. And so this approach might be kind of feasible if you have like a linear classifier, something that's really fast. That's why kind of people use this a lot before deep learning, but we know linear classifiers aren't very accurate. And so basically you couldn't implement this approach today in practice, and like nobody does this anymore. But this is kind of the intuition of how you solve this problem initially, just that you take these individual crops and predict what the pixel at the center of the crop is using exactly the same image classification machinery that we've talked about so far in the course. Okay, so what do people do in practice today? So the breakthrough was kind of this idea that like, okay, so if you take the full image, you can pass it through a CNN, like ResNet or VGG. And remember that what that does is you start out with this image of a given resolution, and as you go through the network, you're downsampling that, and you're also getting more features mapped, so they have greater depth. And so kind of at the end of, say, VGG, your spatial resolution, the width and height, are much smaller than the original image, but you have these layers that are very semantically rich that we use to do things like classification. And so the idea with semantic segmentation is that you essentially stack two of these CNNs against each other. So one is kind of the standard going forward through it, like we talked about, and then you stack another one, which is just going in the opposite direction, and you're scaling back up to the full resolution image. And then you use that to classify each pixel as like cow, trees, grass, or sky. And you just use a classification loss that's defined over all your pixels of that final output of the network. And so this is essentially like a very elegant idea where you're essentially going down through the CNN. At the bottom of it, you get this representation of your data that's very rich in the features that you want to extract, but it's at a much lower resolution, and you want your mask to be in the original resolution. Like when you're in the zoom back, you have a zoom background, like it needs to be like the background in the same resolution as the raw image, right, for it to work. And so the way that you do that is then to have this, essentially this CNN that's turned around backwards. And instead of downsampling, you upsample, but you're preserving those kind of that rich information that you've extracted about the features, that semantically rich information from the first half of the network. And so how do you do this in practice? Well, remember, this is regular convolution, right? You have this filter. So here, this is a 4x4 filter, and you're moving it across the image at a given stride. So here it looks like you're doing that at stride 2. And so you take the 4x4 filter, you take the dot product inside it, and then you move it over 2 pixels. So that's regular convolution, right? And you go from having this this wider and taller layer to having one that is narrower. And you do that a given number of times to get your depth. Well, now we're going to do that essentially in reverse, in something that's called transpose convolution, which I found was like kind of best explained by this figure. And so, like, if you think about doing this kind of, backwards, if you had a 3x3 filter like a filter with 3 dimensions and an output with 5 dimensions, you take it and then you slide it over to. With transpose convolution, you're doing just exactly the reverse, right? So you start out your input. This is like a simplified example, right? But suppose your input is like a 2x1 vector, and then you have a filter that's 3x1. What you do is to multiply the input by the filter at each point. So it's A times X, A times Y, A times Z for your output. And then you need to slide the filter over in your output too to get back to your original dimension. And you do that, and then you multiply by the next input, B times X, B times Y, B times Z. And if they happen to overlap, which they do here, you add them together. You know, whether or not they overlap is going to depend on your original images and the stride you took. But essentially, you're applying these filters to keep kind of that semantically rich information that came out of your CNN, but to upsample that back up to the original resolution so that you can predict those masks. Sometimes in the literature, you'll see this called fractionally shredded convolution or deconvolution. And deconvolution is very common, but that may be confusing if you have a signal processing background, because the term deconvolution is actually used in that literature, which is much older, to refer to the inverse of the convolution operation, which this is not. So just don't get confused if you see that. But this is kind of what this is doing, to take this kind of low resolution, semantically rich output and sample it up in a learnable way. You're learning all these filter weights back to the original image, which will then be trained with the pixel by pixel loss to give you your masks. Okay, So that's semantic segmentation. Does anybody have any questions about how that works? Okay, so I'm going to move on now to talking about the second problem, which is called localization. So remember, localization is you have an image, it has a class, and you know that there's only one object per image that you want to both classify, is it a cat or a dog, and determine its bounding box coordinates. And so again, this is probably not a problem that we might have, although I'm sure it will come up for someone, but it forms a foundation for how we approach kind of more realistic problems. Okay, this problem is going to draw heavily on all the machinery that we've already developed for classification, but it's going to add a fully connected layer at the end to predict the coordinates of that bounding box around your image. So you have an XY coordinate for your center, and then you have the height and the width of the bounding box, and you need to predict those 4 coordinates. And so in order to kind of explain how we do that, it's important to understand that generally speaking in machine learning, we have 2 types of problems. We have a classification problem that has discrete outputs, and that's what we've been talking about so far. Is it a cat, a dog, a car, a train, etc.? And then we have a regression problem, which has continuous outputs. And that's what this bounding box problem is. It has coordinates and they're continuous. And regression here is used essentially in the same sense that we use it in economics. It's just L2 loss. And so essentially the loss on a regression head just takes kind of the predicted value, say the predicted value of that coordinate, subtracts the true value and squares it. Sometimes people use other regression losses for continuous outputs, like a smooth L1, but it's essentially analogous. And so this, when people say a regression head, this is what they mean. It's just a loss, a squared loss defined over continuous outputs. Okay, so recall that in localization, what we need is a class. What is this a picture of? And a location. What are the coordinates of that single object that appears in the image? And the first thing is an image classification problem, and we already know how to solve this. The second thing is a regression problem. We need to predict 4 continuous numbers. And so to do this, we need to remember the analogy we have, which is just that neural networks are Legos. You can stack them on top of each other. And so like with ResNet, right, we've stacked up all these convolutional layers on top of each other. What we're going to do here is take whatever CNN you want, and this is going to be called the backbone. And we take off the end head, which is like a classification head, and we stack these 2 other networks on top of it. And so in this picture here, you see this is a picture that there's a cat, and we want to classify it and determine its bounding box. And the network it's shown here is AlexNet. And then on top of AlexNet, you're going to stack 2 different fully connected layers that use the last kind of layer of AlexNet as the input. So you're going to have a fully connected layer that takes you to 1,000 different classes, and that's the probability of each of the object classes in ImageNet. And then you're going to have another fully connected layer that takes you down to 4 predictions. And those are just the bounding box coordinates of the object. And you're going to do these things kind of side by side and just kind of stack them on top of your CNN. And the reason we do this, remember the point of the CNN is it extracts these meaningful features from your data. And in the basic image classification problem, we use those just to classify, but we can actually use those same meaningful features to both classify and to predict the bounding box of the object. And so now we have 2 branches. They both have fully connected layers, and those layers are used for classification and for regression. So the classification head has fully connected weights. They're going to predict the in-class probabilities. So in this case, it's 1,000, which is what ImageNet is, from the features maps that the CNN backbone outputs. And then you have the regression head, And that's going to just predict 4 numbers. And those are the 4 coordinates of that object's bounding box. Sometimes actually it will predict coordinates for all object classes, but only use the ones for the correct class in the loss. And the regression and classification heads, you could attach them after a fully connected layer, or you could just attach them after the last convolutional layer. And that's going to depend what backbone you use, right? So with BGG, you might have one of the fully connected layers. With ResNet, right, you're going to just attach it after the last convolutional layer. And you're just going to stack these 2 heads, which are what you want to do, on top of your CNN backbone, which is also called like your features extractor. It extracts the meaningful features from your image. So how do we train this? This is what's called a multitask loss, which is very common in machine learning. You have 2 loss functions, a classification loss, like maybe you're using softmax, and a regression loss. And you just add these together, and you have a hyperparameter that tells you how to weight the sum of the 2 losses. So very straightforward. Kind of the only thing to note here is that, remember a few minutes ago when we were talking about, how to evaluate different combinations of hyperparameters, we said, well, you could look at what your loss is. You don't want to do that here because changing this hyperparameter is going to change the scale of your loss, right? You need to look at accuracy or something else to evaluate what this hyperparameter should be. Okay, so that's localization. Are there any questions about any of that? Okay. So I'm going to move on now to talking about object detection, which is essentially like the main meat of what you want to do. Okay. And the first thing, the first question we might ask is, can we just approach object detection as a localization problem? And the reason why we couldn't just naively do this is that our regression head, it's a fully connected layer that has a fixed number of outputs. But how many coordinates we need to predict depends on how many objects are in the image, and that's not known ex ante, right? And so you might have a cat or 2 dogs or a bunch of ducklings, in the case of applications that are more practical to us, you could have very many different objects, depending on the precise layout of your page. And by the way, documents tend to have many more objects per page than natural images. And so that's going to vary, and you don't know that ex ante, so you have no idea like how many outputs you need. And so that's not going to work. One kind of naive approach would just be to apply a CNN to many different crops of the same image using a brute force sliding window. And so this is kind of like the same thing we talked about with the semantic segmentation, about how you could have this sliding window. And we said, well, the problem is that's too expensive computationally if you have a CNN that you're using. Well, that problem is actually like a lot worse with object detection, because now kind of you also have to try different object sizes and aspect ratios for all the different locations. And so this just has a huge number of crops if you did this just naively by brute force through the sliding window approach, and it would be completely infeasible to compute with a deep CNN. And so what people initially did at first was something called region proposal via selective search. And so what this does is just to use traditional image processing tools, like not deep learning, to propose, like, for example, 2,000 regions where objects might be present. And essentially, they're just kind of looking for blobby-like things that could be objects. Like, we're not going to really go into how they do this, because this is like historical. We'll see, this is not what you would do today. This is fastest to run. It takes a couple of seconds per image, 2,000 potential kind of objects is a lot better than having millions of them. And so you just do this and you kind of take all these different proposals for where objects might be. And then you're going to need to resize them. And then you pass them through your ConvNet. And then you put on your bounding box regression and your classification at the end. So essentially for each of these region proposals where an object could be, you're treating each one of them like a localization problem. And the reason that you need to resize it is you have those like fully connected layers at the end that are expecting an object of a given size. So you have to kind of resize it to make the dimensions work out. And so essentially what you're doing here is just doing localization on all these different crops that you think could be objects. And you're going to add a background class because, of course, many of these proposals won't actually be objects. So if it's not an object, it's classified as background. And again, you have labeled data for all of this, and you're supervising this based on the ground truth. And so this was kind of the first idea that people had, and this idea is called like a region CNN. There's a number of problems with this. So first of all, it's pretty slow to train, and like the Regression CNN paper, it took them 84 hours, which is a pretty long time. The way they did it, it took a lot of disk space because they needed to save all those region proposals to disk. They also trained it in a sort of ad hoc way, which isn't too important for our purposes. And then finally, inference was slow. So inference is when now you've pre-trained a model and you want to compute it on new data, like at test time or when you're scaling up. It took 47 seconds per image because you have to make thousands, like 2,000 forward passages for kind of each of these images because you have multiple object proposals. And so that's going to be a really big problem if you want to process like 10 million images and you have a limited cloud compute budget and you need to get it done in a reasonable amount of time. It's actually really slow. You can never use this for real-time things either. And so the solution to this challenge was another paper by the same authors called Fast Rcnn, right? So the previous one was Rcnn for region CNN for cropping these regions. And then they have a next version, which is just called Fast Rcnn. And the insight here is that you don't need to run every single region proposal separately through the ComNet. You can reuse the convolutional features maps, which are expensive to compute. You have these 101 layers of ResNet across the entire image. So the idea here is you still use like the selective search to get your regions of interest, but you just essentially project those through the ComNet. And those give you your region proposals. Then you resize them using something called region of interest pooling, pass them into your fully connected layers, and then you can get your, you essentially have your localization problem where you have your classifier for object type and the bounding box regression. Okay, and so what you're doing here is you have your CNN, you're using it to kind of extract these features. So like with ResNet, you're just chopping off the last classification layer. And you have this network that's fully convolutional. And this is important because a fully convolutional network, unlike a fully connected layer, can just take inputs of any size. And of course, we want to process images of different sizes, and so this is important. So this can take in kind of images of any sizes, and then we'll figure out where they are on this features map that it outputs. And then we'll make it a fixed size for our fully connected layers at the end that do the classification and regression. And the way that they do this to turn this into kind of these fixed size objects that the last layers require is to just to crop the convolutional features map using each of the proposals. So you can project that proposal from the raw image to the last layer of your convolutional features map. And then you're going to resize it like using interpolation and maybe pass it through max pooling. And that will give you this constant sized input to your classification head and your regression head. And so this is just an example of what this would look like. And so let's say that you are trying to identify the bike and the person in this picture, and you have a region proposal that's kind of overlapping the bike. Well, you can figure out where that is in the last layer of your ComNet, which you see is the red there projected down. And then you do the region of interest pooling to get the fixed size output that you need in order to run your classification and regression. Okay, So I'm going to just finish this topic quickly. And so after you've extracted the features of each proposal, the region-based CNN just mimic the final stages of classification CNNs, where you have the classification, and then you have the regression layer, which is going to take that proposed object and it's going to adjust the coordinates. It's going to estimate an adjustment to each of those 4 coordinates to make it more accurate. And so we've just essentially turned this into a localization problem on each proposal. And so in terms of how you train this kind of in practice, you take proposals that have a certain intersection with the ground truth, and those are proposals that have an object, and those that are below some threshold intersection with the ground truth are classified to background. Then you're just going to take these proposals and sample a mini batch from them. And so you think of each of these proposals almost as like a different image that's going through your classification and regression network, except you're not recomputing the COMNet each time. You're getting it from the final features of the COMNet, but you think of each of these regions of interest as a mini batch. And then you have your multitask loss at the end, where you have the weighted sum of the classification and the bounding box losses. And so we're out of time, so I'll wrap up for today, but we'll come back and we'll re-summarize what this fast Rcnn is doing next time, and then we'll talk about kind of the potential problems with it and how they have been subsequently fixed by the literature. All right, thank you guys.